Welcome back. This is part 2 of the 2.6 notes, and we're just going to kind of continue where we left off. So what the next question is asking us to do is examine example 2. So what we graphed at the absolute value of x plus 2 over x plus 2. It says, at the point of discontinuity, does the limit exist? Would it exist from only one side? So if we were going to look at, does the limit as x approaches negative 2 of f of x exist, we would need the function to approach the same value from the left and from the right. Well, in the graph above, as we approach negative 2 from the left, we're approaching a value of negative 1. And as we approach negative 2 from the right, we are approaching a value of positive 1. So those values are not the same, meaning the limit as x approaches negative 2 of f of x does not exist. Now, it also says, would it exist from only one side? That answer is yes. If we were to look at the limit as x is approaching negative 2 from the left of f of x, we would approach a value of negative 1. And the limit as x is approaching negative 2 from the right of f of x, we are approaching 1. So it's really important to understand that just because the limit does not exist does not mean that the one-sided limits don't exist. So, little reminder of notation for one-sided limits. If we're looking at one-sided limits from the right, we are going to use the notation that looks like this. The limit as x approaches a value a from the right of f of x. And if we are looking at a left-sided limit, or left-handed limit, we're looking at the limit as x approaches a from the left of f of x. So it's definitely important that you guys get familiar with the notation so when you see it, you understand what a question is asking. All right, so we have some more examples here. So in example 3, it's asking us to find the one-sided limit. And in this case, we want to know the limit as x approaches 4 from the left of the square root of x minus 2 over the quantity x minus 4. Now, it does say no calculator, and this can get tricky. Things you might want to think about is, what does this function look like graphically? And that might help us kind of get a picture of what's going on. If we could plug it in our graphing calculator, we could use the graph to quickly answer this question. But on a no calculator problem, let's see what we can come up with from the graph, or for the graph, I should say. So just analyzing the function, it's rational. I've got x minus 4 in the denominator. That is not a factor of the numerator. So one thing that tells me right now is that this graph, or this function, is going to have a vertical asymptote at 4. So I'm going to start by plugging that value in. So I've got a vertical asymptote, and what I know is that my function is going to approach that asymptote from the left and from the right. It'll never get there. So the question we really have here is, does it approach it from the left? Does it approach it towards infinity, or does it approach it towards negative infinity? So we could pick some values of x and just kind of evaluate this function. And specifically, we can focus just on the left side of 4. So let's try 2 and let's try 3 and see what we can come up with. If x is 2, the square root of 2 minus 2 is 0. So that's going to be 0. 2 minus 4 is negative 2. 0 divided by negative 2 is 0. So there's going to be 0. If I plug in 3 for x, I've got 3 minus 2, which is 1. The square root of 1 is 1. And then the denominator is going to be 3 minus 4, which is negative 1. So 1 divided by negative 1 is negative 1. So at that point, I've got a pretty good idea of what this graph is going to do. It's going to approach that asymptote going down towards negative infinity. So I can go ahead and answer my question. The limit as x approaches 4 from the left of the square root of x minus 2 over x minus 4 is negative infinity, which really means it does not exist. Now, some things that are worth noting in here. I could plug in some other values that are going to be larger than 4 to see what's happening to the right. But I didn't need to focus on that here. Something else that's important to remember for problems that are going to come up later is my numerator is a square root function. You cannot have negative values underneath the square root, which means that the domain of my numerator is going to restrict the domain of this function. Only values that are 2 or larger can be within the domain. So there would be no points to the left of this point right here at 2, 0. So we wouldn't need to worry about anything beyond there. Okay, let's take a look at the next example. So here we have a piecewise function. We have the limit as x approaches 2 from the right. So that plus is what's telling us we want to know from the right. So using values that are larger than 2. So I've got the limit as x approaches 2 from the right of this function. So in a piecewise function, I've got to take a look at my restrictions. So I've got x is less than or equal to 2. Well, those are going to be to the left. I've got if x is greater than 2, those will be to the right. So that's telling me I'm going to use the bottom function. So I'm going to go ahead and say 2 squared minus 3 times 2 plus 12. And all I'm doing is substitution at this point because the function's defined. So 2 squared is 4, negative 3 times 2 is negative 6, 4 minus 6 is negative 2, plus 12 is positive 10. So the limit as x approaches 2 from the right is positive 10. All right, moving on to the next example. So, these are just kind of some reminders. It says a limit exists only if the limit as x approaches c from the left of f of x is equal to L, and the limit as x approaches c from the right of f of x is equal to L. So the left-handed limit and the right-handed limit have to be equal for that limit to be equal. So if we wanted to find the limit as x approaches 3 of this piecewise function, what we're going to need to do is find the left-handed and the right-handed limit and see if they're equal. So for the left-handed limit, the limit as x approaches 3 from the left, I'm going to use the top function. So that's going to be negative 4 times 3 plus 7, which is going to give me negative 12 plus 7, which is negative 5. If I use the right-handed limit, the limit as x approaches 3 from the right, I'm going to use values that are larger than 3, which corresponds to the bottom function. So I'm going to have 3 squared minus 3 plus 1. 9 minus 3 is 6 plus 1 is 7. So you have the left-handed limit and the right-handed limit that are different, which is going to tell me that the limit as x approaches 3 of this particular function does not exist. All right, for the next example, we want to look at using the definition of continuity to decide if a function is or is not continuous at a point. So a little reminder, here's the definition. It says a function is continuous at x equals c on the closed interval from a to b if it is continuous on the open interval from a to b, and the limit as x approaches c from the right equals the limit as x approaches c from the left equals the value of the function. So what I'm going to do is, if I want to try to determine, using 6a, use the definition to decide if this function is continuous at 2. The first thing I want to do is see if the function is even defined at 2. Because if the function is not defined at 2, it cannot be continuous. So I'm always going to start there. So if I wanted to go ahead and evaluate this function at 2, I need to find the part of the piecewise function that tells me what happens when x is equal to 2. Well, if you take a look here, you have one restriction that says x is less than 2. You have another restriction that says that x is greater than 2. Nowhere is there an equal sign. So that means that h of 2 is undefined. And if a function is undefined, the function cannot be, or undefined at a point, the function cannot be continuous at that point. Okay? So, since I'm just going to go ahead and say h of 2 is undefined, therefore, h of x is not continuous at x equals 2. All right, now 6b takes that same function, but this time it tells us that x is less than or equal to 2 in that top function. So that's going to change the problem a little bit. So what I'm going to go ahead and do is same thing. I'm going to start by finding h of 2. So h of 2, okay, I'm going to use the top function when x equals 2 is going to be negative 1 half times 2 minus e to the 2 minus 2. So that's going to be negative 1 minus. Well, 2 minus 2 is 0. Anything to the 0 power is 1. So I end up with negative 1 minus 1, which is negative 2. So this time the function is defined at 2. Now I need to know, is the left-handed limit equal to negative 2, and is the right-handed limit equal to negative 2 as well? So for this problem, the left-handed limit is going to be found using the same exact function that I found h of 2, because those are values less than or equal to 2. So this, I'm going to go ahead and just say, is equal to the limit as x approaches 2 from the left of h of x. And then I don't have to redo all those calculations. So next thing I'm going to do is I'm going to find the limit as x approaches 2 from the right of h of x, which in this case is going to use the bottom function. So 2 squared minus 6. Well, 2 squared minus 6 is negative 2. So what we can now say is the limit as x approaches 2 from the left of h of x equals the limit as x approaches 2 from the right of h of x equals h of 2. Therefore, h of x is continuous at x equals 2. All right, guys, that's going to end part 2 of the video, but look for part 3 that will continue on with these notes.